All right. Can you see that?
And yes, but it's not in presentation mode.
Okay.
All right. Looks good. So,
see all that?
Yep.
Okay.
Looking good. All right.
Cool. Okay.
Fantastic. Well, good morning, everybody, and thank you so much for joining us today. We are here to honor the work of these undergraduate students. This is the It's a Science Thing panel, and we have 3 presenters today. And so just a little bit of housekeeping before we get started. For all of our non-presenter guests, please make sure that you're muted with your video off for the duration of the panel, and please be respectful of each other and the presenters. And thank you so much for joining us today. For the presenters, please also remain muted unless you are presenting or responding to questions during the Q&A, which will take place at the end of all 3 presentations. So the Q&A will be at the end. Each of the presentations will be somewhere between 10 and 12 minutes long, and then at the end of all 3 of them, we'll have plenty of time for Q&A. And so I will be keeping time here, and I'll give you a little bit of a nudge at the end after 12 minutes to be, okay, come on, let's wrap it up here. And so, and then I will help guide Q&A at the end here. I also failed to introduce myself. I'm Franny Gaede. I'm the head of Digital Scholarship Services in UO Libraries, and my compatriot here helping with Zoom moderation, the very important technical pieces, is McKenzie. McKenzie, would you unmute and introduce yourself?
Of course, thank you, Franny. So I'm McKenzie Winder, she, her, hers, and I work with the Orientation Programs Department on campus, doing important pieces like Introduction, Week of Welcome, and of course, all of our family events throughout the year right now. So happy to be a part of this, and I'm looking forward to hearing from you all.
Likewise. Thank you, McKenzie. Last piece is that we are being recorded right now. We are not live streamed, but at the end of the symposium, that these presentations in the Q&A will be made available for others to watch. So just so you know. All right. So first up will be Jeremy with Time Spider, characterizing the electric field of pulsed lasers. So take it away, Jeremy.
Thank you. Hi, my name is Jeremy, he, him, his. I am undergrad working in Brian Smith's lab, of which is affiliated with the OMQ in the UO Physics Department. Our group specializes in working with lasers. So appropriately, I'll be discussing interferometry. SPIDER is an acronym, so also, unfortunately, we won't be talking about arachnids. So, understandably, I attract a lot of confusion when I'm asked about my physics research, and I respond with, I work with Time Spider. I'm going to clear that up. SPIDER stands for Spectral Phase Interferometry for Directed Electric Field Reconstruction, which is, it's a pretty gnarly definition, but truthfully, SPIDER is actually quite simple. Laser pulses are defined predominantly by something called the electric field. We want to know, we know this from theory. We also know how to create laser pulses without knowing its specific mathematical description. Our goal with SPIDER is to fill in this missing puzzle piece and mathematically describe the electric field of a laser pulse. Okay, but what is a pulse? Think of a pulse as your motion when in a wave in the ocean. You rise and then you fall. For our purpose, this is an accurate way to describe a laser pulse. Below Kelvin, we have a theoretical laser pulse's electric field. Observe it roughly follows the same wave analogy from before. It has a rise and a fall. And if here, let me just try to use, actually, you have to respond to this, but hopefully you can see this. I have a laser point. So it actually, yeah, you have this sort of rise and you have this fall. Okay. focusing less on the math, uh, we're just gonna talk about how it works in a physical sense. So back to the acronym, SPIDER is an interferometric approach to mathematically describing or characterizing the electric field of the laser pulse. What this means is that SPIDER is like a machine, such that when you shoot it with a laser pulse, it then outputs a new distorted laser pulse that carries our desired information. We then measure the distorted pulse with a spectrometer. And so after that's all done, we can then just use math to do the heavy lifting to finally describe the initial laser pulse. I won't get into the math, but if you want a taste of it, we have some right below the diagram. SPIDER works as follows. The desired pulse is split into two via a half-silvered mirror. One pulse is given a time delay, while the other is given a frequency delay. In a more physical context, one pulse may take a longer path to go from blue to blue being the half-silvered mirrors, and this would be considered to be a time delay. That's a really easy thing to do, especially in an experimental context. You can always just get more table to to have more of a time delay. On the other hand, the other pulse would have to have its color changed, and that would be a frequency delay, and that's much more difficult. So, okay, this is great. We already have a good method for characterizing pulses. Why would we need to introduce this new word time into SPIDER? Why the time SPIDER? Well, the main issue comes from when we try to modulate the change in frequency. So it all comes back to changing the color. Generally, in a SPIDER setup, we will have a pulse duration of about 100 femtoseconds. To get a better idea of how fast something like that is, 100 femtoseconds is roughly the length of time it takes for light to travel the thickness of a hair. So we're dealing with really precise things. The visible spectrum is about 400 nanometers, and the bandwidth of our spectrometer would generally be about 10 nanometers. So our pulse may be, let's say, like a very specific shade of blue. The frequency shift would be about 1 nanometer, which is extremely precise. That'd be like if we had 100 colored pencils and we had to isolate specifically one of them. The longer the pulse duration, the more colored pencils we have, until at some point we just can't even resolve it, and it becomes too difficult of a problem. The main point is that time delays of any length are easy, and precise frequency shifts are hard. So the time delay that you need for SPIDER is roughly 10 times the pulse duration, meaning the frequency shift is 1/10 of the pulse's spectral bandwidth. Once our pulse duration increases to around the sub-picosecond regime, we start to have resolution problems in the frequency domain. So the sub-picosecond regime would be most people would say that's about right before things start to get ultra fast. We don't have an ultra short laser pulse. So, okay, what's the proposed solution? Measure the electric field in the time domain instead of the frequency domain. Now we have a complete swapping of the roles of time and frequency. This means that the roles of time delay and spectral shift are swapped. So, if we have a large spectral shift and a small time delay, then those things are inherently swapped as well, and that's something we can work with. This new method is called time SPIDER. Time SPIDER would stand for temporal phase interferometry for direct electric field reconstruction, which really is not an accurate. So, I mean, it would have to be T-PIDER, but that doesn't make sense. We're still looking for a better acronym, but you get the general idea of it. We're just, instead of measuring it in the spectral domain, which would have been SPIDER, spectral phase interferometry, we now use time. So another good thing about time SPIDER is that you don't really, there are many methods, there's generally two classes of characterizing, of things to characterize pulses. One requires iterations. So you're basically, you gotta wait for it to go over, to iterate until it can finally resolve this this pulse over a long period of time. And then there's ones that are just direct reconstructions, and that's we're talking about a direct reconstruction. So generally, Spider and Time Spider, they don't require iterations to get a good approximation. You can just press a button. The unfortunate thing is that it requires knowledge about the type of pulse that you're working with. So we're limited by the pulse that we want to characterize. That does require information about the pulse that we may not have had earlier. But the good thing is that since these are direct measurement techniques, as long as you can have both Spider and Time Spider, you have a lot more flexibility in the lab. So possible ways that this setup can be created would be using something called perhaps well, okay, so first, the easy part, as we mentioned before, would be the time delay. The time delay is just, you got to increase the amount of space you have on the table, but that's not a problem. The spectral delay, maybe you'd use an electro-optical modulator or an acousto-optical modulator. Regardless, that's an open question, and we look forward to addressing it in the future. The important thing is that this really does build on a lot of concepts that that are important in physics in general. So metrology, which is the study of measurement, that's incredibly big. It's an incredibly big field of research. A lot of our experiments in the lab require information about the phase. So if we can have a flat phase, for example, then a couple of experiments would be, we would be able to continue. So for example, two photon oh, why am I blanking on this word? But yeah, no, we have a couple of experiments that required this sort of information, and generally you want to be able to make precise measurements. So if you know the type of pulse you're shooting, then that's always better than not. The math is not very hard. It does require some background, but after the hard part really is to just build the thing. I think that concludes my presentation. Yeah, there we go.
Fantastic. Thank you so much, Jeremy. And we've still got a minute and some seconds left on the clock. Thank you very much for keeping time. Wonderful. Well practiced. And up next, we'll have Jake with the atomistic reconstruction of coarse-grained polymeric systems via machine learning techniques. And Jake, you are muted.
There we go. Okay. Sound okay? Hello?
Sounds good. I muted myself.
Okay, cool. Sounds good.
All good.
Well, hello, everyone. My name is Jake, and I am a fourth-year student here at the University of Oregon, and I work in the Guenza lab, which is a computational chemistry lab. And today I hope to be taking on a journey and give you some insight into the very unique and interesting world of computational chemistry. So to start, I want to talk about why do we need computer simulations? And to try and understand this, I want you to take a quick second to look in the room around you and consider your laptop, your phone, your water bottle, whatever is surrounding you, and realize that our world is completely filled with these different synthetic materials that we create. And these things are very, very difficult to investigate if we want to create new different types of materials. Similarly, our bodies and the world is also made up of various biological systems that are very, very important to investigate, and it'd be very great if we could look at these on the microscopic level. And furthermore, drug discovery is a very, very technical and difficult industry, and it would be very, very useful if we can somehow speed up the process of drug discovery without having to produce stuff in lab. And so that's where computer simulations come into play. We're able to look at these different types of systems with very, very time-efficient manner. And one of the ways that computational physical chemists do this is by using something called molecular dynamics simulations. And so what molecular dynamics simulations are is they're a way to look at the time behavior of a polymer system. And so my lab looks at various different types of polymer system. Here on the right, we have a polyethylene molecule jiggling around. Generally, I would show you an entire simulation, but it kind of looks like a mess if I go to any more than one polymer. But what MD does is we solve Newton's equations for some given amount of time to find all the forces on the atoms. And then if we do this for across multiple time steps, we get a trajectory of the atom, and we get to watch it evolve in time. And so if we, with well-defined potentials between the atoms, we can basically model any system that we want, which is super useful in this idea of trying to model things like biological systems. But one of the unfortunate things with molecular dynamics is that the amount of computational time it takes to do these simulations grows with the number of atoms squared. And so this is very, very costly if we want to investigate big systems or look at these systems over a long period of time. So one way we can try and solve this is using something called coarse-graining. And so what coarse-graining allows us to do is it allows us to reach a new time scale or a new length of time to investigate various system properties or systems of really, really big sizes. And this allows us to look at things like diffusion or glass transition states or morphology or other various properties that depend on being able to simulate for a long time. So what coarse-graining specifically is we reduce the amount of degrees of freedom, in this case the number of atoms, by grouping sets of atoms together into blobs or CG sites. And so as you can see in the figure to the right, we have a polyethylene chain of a length 192, and each 32 polyethylene units gets condensed down to one blob located at the center of mass of all those sites. And since this grows with n squared, if I reduce the number of atoms or the number of sites by a factor of 32, going from 192 to 6, we increase the computational time by almost a factor of 1,000, which is really, really important for trying to conduct these types of simulations. And we can remain just as accurate. However, we do lose some statistical information on the local length scale. And so for this, we need to do something known as backmapping. And so the goal of backmapping is to try and regain that lost statistical information. And this would be super useful because now we can investigate systems with really high speed and very fine accuracy. And so here on the left, I have a rotating diagram of trying to reinsert atomistic information. So in the very light blue, we see a very coarse chain of just 6 line segments. And we want to reinsert that atomistic information to get to that blue, dark blue configuration. So the system that I look in my lab, I think I've previously mentioned, is polyethylene. And specifically, we have 350 of these polymer chains with 192 monomers. The monomer unit is shown in the figure, where it's just these 2 carbon atoms with 2 hydrogens attached. So it's the most basic polymer system. And it's really, really useful to investigate because it's so ubiquitous. Basically, polyethylene is the most universal plastic in the world. And so one of the big uses of coarse-graining and backmapping is it allows us to do something called adaptive resolution simulations. And so here we can see on the left and right, we have these coarse-grained polymer beads. And then in the center, we have these atomistic sites. And then in between those two, we have this sort of interface between these two systems. And therefore, we can model this system and be able to easily transition between these two representations and improve computational time by coarse-graining different areas that aren't as useful to investigate on local length scales, and we can keep high resolution in the areas that we do care about. So the way that my lab decides to do this is using machine learning, because this is not a trivial type of thing to do. We've tried many approaches to try and do this, but it's very, very difficult. Luckily, we've come upon this machine learning method where we try and rebuild one blob at a time. And so this is 32 sites within one blob. And so to the right, we can see that we're trying to grow this molecule inside some blob, where the blob is represented by the little red dot. And so the model is receiving all this different atomistic information along its positions of nearby blobs, and as well as the other blobs on the same chain, to try and give the model the ability to try and grow the correct chain's characteristics. The way that we do this is we're using Python 3 with TensorFlow, and we're using some very technical things called a gated recurrent unit, which is a type of recurrent neural network. But basically what this allows us to do is as the chain grows, it can keep an idea of the previous sites and have some information about what the chain is doing as it grows. And we use something called a categorical cross entropy loss function. And essentially what this allows us to do is have more flexibility with our model. So hopefully this shows that this is a very, very effective method to try and regrow these sites. And so getting into some of the results, this is something called the loss and the validation loss. And essentially it's a measure of how good our model is learning the different characteristics. And so since it's continuously decreasing, it shows that our model is getting better and better, and it's approaching a minimum. Also, we see a very good agreement between the loss and the validation loss, which is just a very important characteristic for a model to be considered good. So moving into some other characteristics, I'm going to just quickly show some diagrams of what the characteristics that we often look at. So here on the left, we have the bond length, which is just the measure between two atoms, the bond angle, which is a measure of something between three atoms, the dihedral angle, which is a correlation between four atoms, and then finally we get up to something like end-to-end distance, which is the measure between the first atom and the last atom. So we look at all these different characteristics of the chain. So to start, we're going to look at some of these quantities. So for example, on the left, we have the bond length, and we see very, very strong agreement with the atomistic simulation with the predicted. And the predicted is what our model is producing. We see some weird behavior, and we can talk about that later, but it's just a result of the system, and it's not super influential on the actual results. And we see pretty strong agreement between the end-to-end distance, between the atomistic and the predicted, which is really good because it shows that our chains are behaving correctly over a long distance. And then furthermore, we also have very strong agreement between the bond angle and the dihedral angle. And so once again, we're seeing that the model is accurately able to reproduce these atomistic systems and get the improvement of coarse graining and backmapping. Finally, we also see some more global properties, such as the distance around the blob center, or basically the distribution, and we see strong agreement there. And in the diagram on the right, we have something called the mean square internal distance. It's not super important for you guys to understand what this quantity is, but essentially it tells us how the local and large length scales of the polymer chain are behaving. And we see very strong agreement between the atomistic and the predicted. And the red line above is a theoretical model that it's often under approximated by atomistic simulations. So finally, I'm going to show you a quick illustration of what our model kind of sees and produces. So this green chain is the predicted sites, and the red X's is the original atomistic sites. And we see that there isn't immediate overlap, but this green chain still produces the correct statistics. And that's because when we lose all these degrees of freedom by going through coarse graining, it's impossible to actually get back to the original chain because we lost so much information. So we mostly just care that we're getting the correct characteristics, and we can see that it's able to grow this chain with very, very similar characteristics as the original chain, which is very, very good. So talking about trying to sum everything up, what we see is that this model is able to accurately produce a blob configuration. And so hopefully we'll be able to extend this model in the future to reconstruct entire systems and entire polymers. And this would allow us to do things like adaptive resolution simulations, where we can easily transform between AT or atomistic and coarse-grained representations, and the other way as well. And this really helps us improve computational time and allow us to investigate systems that we were never able to investigate before. And so this is a very, very powerful tool, and I hope that I've shown you the very, very cool world of computational chemistry and the amazing applications it can have. So with that, I'd like to thank you for your time, and also thank the Undergraduate Research Opportunity Program for awarding me the PChem Fellowship and allowing me to become a member of the Presidential Undergraduate Research Scholars Program, which has helped fund and give me all sorts of resources that you conduct this type of research. I'd also like to thank Professor Marina Guenza and Dr. Jake Searcy, as well as the other members of the Guenza Lab, for supporting me and helping me throughout the entirety of this project. And with that, I thank you.
Fantastic. Thank you so much, Tim. Jake, sorry. Thank you. All right. Up next is Tim with Peirce's Phenomenological Grounding of Science and Matters Therein.
Hello. Let me quick get this up. All right. Hi, my name is Timothy Schatz, he, him, his. I'm a math and philosophy fourth year undergrad student, and here I am presenting the preface to my thesis on Peirce's phenomenology. And as that is like around 70 pages, there's no way that I can really condense that into any meaningful way. So I had to just pick a section and go. Okay, so in the movement of inquiry, we have not merely to begin with nothing such that we simply look outside and see the truth. For consciousness is always of a particular shape. This ideal of the objective nothing of scientific consciousness, that is, the positivist empirical subject, if it were to manifest, would not produce a result at all, for it is a nothing, and so will result in a nothing. As Heidegger says on the topic of inquiry, every inquiry is a seeking. Every seeking gets guided beforehand by what is sought. Inquiry is a cognizant seeking, both for an entity, both with regard to the fact that it is and with regard to its being as it is. This cognizant seeking can take the form of investigating, in which one lays bare what the question is about and ascertains its character. Any inquiry as an inquiry about something has that which is asked about, but all inquiry about something is somehow a questioning of something. So in addition to what is asked about, an inquiry has that which is interrogated. As such, when science sets out to discover the underlying matter, the something of inquiry, it is done in such a way that the truth, the result, can only be revealed in a certain manner from already chosen objects. In this way, any doctrine, any particular shape of consciousness, has already set the horizon of its world. We must remember the origin of the word truth in aletheia, unconcealment or disclosure. Truth is not so much something that is simply apparent to the seer. Instead, truth is revealed, disclosed in the act of seeking. And in this way, only when we have set out as a seeker do we find the truth. The scientist, in their seeking, thereby has the object disclose itself as a particular phenomena according to the manner of seeking. Here Heidegger is instructive once more. For phenomenon, of which phenomena is an instance of, signifies that which shows itself in itself, the manifest. Phenomena, which is what is here, is that which appears before us and is thereby conditioned by our comportment. However, this is not to say that we are a sort of being that brings forth the world from mere thought in a manner which we could say that the world is determined by thought or conjured by thought. Instead, it is that the world appears before us as co-constituted. Hence, when the scientist sets out to discover the truth, they condition the object of study, and so condition the result. That is, they condition the unconcealment of truth. How does the scientist seek? Here is not such an easy question to answer, for it is not that the method is sufficiently developed as to need lengthy volumes, but that since when science follows its basic principles, it takes shape in near infinite variety. That is, the work of the chemist is not the work of the biologist, nor is it the work of another chemist. However, it can be said that its guiding principle is falsifiability, insofar as when the scientist sets out with a hypothesis, it is one that is testable. Here a scientist approaches their object with an ideal of subjecting the object to a manner of examination such that the object is made to say yes or no, or it reveals itself to be such that it either is or is not that which it is thought to be. Yet the error of science is not that in the unfolding of its method, dogmas appear which cling to insufficient evidence and snuff out the light of other theories that are said by some to be better. Rather, it is that in approaching the object, the scientist has already said that the object ought appear as something predictable, regular. For the scientists, objects are mechanistic, governed by absolute mechanical laws. These mechanical laws are powerful, for they indeed reveal a truth about the object. For if I were to drop an apple or set up some elaborate scenario, I would be on good standing to say that a series of calculations will give me insight into what will happen. It is not the positing of laws, it is not the having of a theory that is the error. Rather, it is that admixture of falsifiability, mechanical law, and science's own history of success that contains the error of science. In the setting up of the mechanistic laws, they are taken to be universal, as an articulation of the object's essence. But since these laws are the universal, the totality of the cosmos's being is made self-same. That is, the past, the present, and the future all possess the same being. This is due to the fact that the mechanical law treats time not as time, but as space. And so any event can be merely wound up or unwound according to whim. If this were merely said of the past, then little should be said, as in, this happened and before it another thing happened, i.e. a narrative. But when a scientist inquires about their object, it is unconcealed only as a mechanical being, which holds its past and future in its present, and its present in its past, and so on. The object is made to speak a language which does not come from the communion between the scientist and the object. Rather, the object is compelled to disclose itself in an alien manner, and so much is lost in translation. It is not that nothing is said, but that only which is sayable in the language of mechanistic law is said. Hence, in no way is it claimed that science doesn't reveal anything true. Rather, it is when science, and here it is meant in the contemporary sense, is taken as the mode of knowing that the error exists. The error, which can now be articulated, is that science takes its composure, its manner of inquiry, as the only correct mode of seeking. Every disclosure also encloses. To be open in one regard is to be closed in another. No single inquiry can ask the question that will unconceal the world in a manner which the sun prompts the bloom of the morning glory. Here, the truth of the object is disclosed to the scientist in accordance to which is brought into the light when seeking the mechanistic part of the essence of the object. This as part of the essence is therefore not the essence. The error of science is that in saying that anything which is not of that essence is not of the essence at all. What science cannot answer over time is called irrelevant or irrational. Here follows the great disenchantment of the world, and as long as science maintains to ignore how it comports itself into the world, it will only continue to be the henchman of ecological destruction, the offuscation of the divine, and the desiccation of the human spirit. However, this error is not the end of science. Rather, it presents itself as a moment of development for science. As such, we can ask the question anew, how are we to investigate the world? Here, Charles Sanders Peirce's Phenomenology provides an answer, for it does not take thinking about thinking as its mode of inquiry, nor an absolute method, but turns to the world and contemplates the manner in which it appears. For Peirce's phenomenology is the means by which one draws up the list of categories that structure the mind through articulating what presses upon the mind. Thus, when I look out and see a yellow flower, I have formed perceptual judgment, the proposition, the flower is yellow. And so I have utilized the categories of my cognition to form the proposition such that they have been encoded within. But we do not know the categories by analyzing the statement itself, but instead by studying the formulation of the statement. From this, Peirce derives his three categories: firstness, secondness, and thirdness, alternatively, quality, relation, and representation. This triad, understood in itself, is very abstract, but in an example, it is quite natural. When I look at the flower, the entire scene, the entire contents of my consciousness, from sight to sensation to emotions, is a simple unity. Such is firstness, for it has a quality of feeling to it. However, each thing, each bundle of feelings, is also not an other. That is, throughout levels of analysis, here is the diversity of qualities. This is the category of secondness, that silent resistance, that looming presence of something other, the relation to another. Hence, the flower per se is in relation to the other qualities of the ground and the sky. Therefore, cognition possesses near infinite demarcations of quality, which are all present through their relations. Hence, thirdness is the continuity between these opposed firsts, such that the quality of the flower and the quality of the ground in continuity is represented as the flower planted in the ground. Thus, pictorially, firstness is a mere dot, secondness another dot, and thirdness the line that joins them. Therefore, for Peirce, cognition possesses this fractal structure in which any triad can become a first for another, and so on. However, what is revolutionary about Peirce's philosophy is not the categories per se, rather is that the categories, while they are of mind, are themselves in continuity with the structure of reality. It is not that reality is the same as the mind, but that the real world, in being cognized, is necessarily in continuity with its appearance in the mind. It is not that we have certainty of the truth in that when the object discloses itself to us, but that we have a connection to the thing in itself, which is unconcealing itself before us. These categories thus form the divisions of knowing, or science in the old notion of Wissenschaft, in which the special sciences, i.e. the contemporary sciences, are those manners of knowing which pertain to thirdness. For thirdness is concerned with the formulation of laws, representation of what is, in the sense of building models. Hence, in going to phenomenology as the wellspring of truth, science is attentive to the manner in which the object is disclosed, such that the vast fields of study thereby arise following the different manners of disclosure. In this way, phenomenology forms a new ground for science, in which we are no longer subjecting nature to the order of nous, the order of mind, but instead listen to nature, such that it discloses itself to us. Thank you.
Wonderful. Thank you so much. All right. Well, we have plenty of time for questions here. So if our guests would like to enter questions into the chat, or if our panelists have questions that they would like to ask of each other, more than welcome to do so. Give a few moments here for typing.
I have a question for Jeremy, if that's okay.
Absolutely, please.
Yeah. So Jeremy, when you're like, so you're measuring, like you're looking at the interaction between two separate pulses, right? Like one with a time delay and one with a frequency delay.
Yep.
So when those waves then re-interact, do you have like any sort of like convolutional effects when they?
Yeah.
Okay.
No, that's exactly it. Yeah.
Okay. So
No, sorry, keep going.
no, I was just go for it. Yeah.
No, yeah, no, it really is just a convolution. You have these two interfering waves, and then you end up taking a Fourier transform of the two. So from there, you then have three different waveforms, and you're basically just using a Hilbert transform to then extract the phase from that point, and then you can do inverse Fourier transform, and then you have the phase.
Okay. Cool.
So have a question here. Tim, do you think it's a generalization to say that scientists view science or the scientific method as the mode of inquiry par excellence?
I mean, I think that's pretty, I would say yes. I mean, it's not that there's a problem with falsifiability per se. As I said, it's this admixture of its own success that in a sense can become blind to its own manner of operating. Really, I think if scientists are appropriately aware of how it is that they're approaching the object in the way that the object is revealing itself, then I think that the error basically subsides. Like, it's not that nothing true has been said. Like, clearly, look at the technology. We're on a Zoom call. Something true has been revealed, but the question still remains as to the question still remains as to, I guess, how we're going to continue to reveal the object, especially in the light of, and I want to say that the ecological destruction and certain problems of instrumental reason.
Thank you. Another question from Scott Pratt. Thank you all for your presentations. As a philosopher, I'm interested in the ways in which philosophical examination can address issues in the actual practice of science. So to Timothy, what does your take on Peirce have to say about the inquiries conducted by Jeremy or Jake?
See, that, yeah, I was thinking about that throughout the presentation. So it's kind of funny. All the philosophy people were kind of thrown around through a variety of different categories. So, I'd say, like, I guess, like, the question I think really starts to be of, like, what starts to be done with the research, and like how is it taken, and at what point is a model start to be mistaken for what's actually going on. Like you talked about, I believe that Jake talked about how they would create the model, or they would create the computer algorithm, the AI learning software, to get a better idea of what's going on. And insofar as it gives a better idea, that's good. But the thing is that in going to a computer learning software, into a computer learning model software, I'm not sure the correct terminology to use here, there's still the black box problem of what is it doing? Is that there's this disconnect and just this appearance of something, and it becomes purely correlation of it produces a similar enough effect, and so we don't consider what could be going on in the process of the algorithm churning on the data. If that, I think, I don't know, what do you think, Jake?
Yeah, so I understand what you're saying. I guess in response to that, like, so that's kind of like the study of science. Like, there is no fundamental way of knowing how the world works. Like, that's just fundamentally impossible. The goal of a scientist is to design a model that works and then try their hardest to disprove that model. Like, famously with quantum mechanics, Einstein has said that quantum mechanics is incomplete and we need to either try and fix it or prove it wrong. And so, like, that's kind of like the goal of science, is like we do create models and we do get into using them, but that's kind of all we care about. It's like everything we've done is make a model and see if it works, and if it continues to work, then we're going to continue to use it. So I guess, like, I kind of struggle to see, like, how we're going to somehow try and find the actual truth when there is no way of actually doing so.
I mean, I maybe want to say, like, what is the model doing then? It's somehow, there has to be some truth which is being touched in a manner. Otherwise, there would seem to be nothing hard, nothing to be pushing against. Like, at least the real world, you know, if we're going to go with like Peirce's notion of it, or the real presents itself in that category of resistance, of secondness, of when I go out to push a wall, the wall pushes back on me, and there's something true in that. And so the model, we can model this, we can model something more complicated, but it's still modeling something. And it has to be modeling something. And that something contains a truth. So in that way, we can't really ignore the question of truth, but that it's always going to be in there, and it's a question of how we're letting the truth speak.
But we'll always be modeling the truth. Like, that's the fundamental notion. So, like, in the case of like the AI, like, you do make a good point, like, it is a little bit of a black box, but there are a lot of fundamental things that we can do to look at how it performs in the specific ways that it is producing its results. So it's not completely a black box. Like, we can conduct some research in terms of trying to find how it behaves and what it's specifically doing. I guess it's just like, it's interesting to me to look at it that way, because every model is, like, every way we look at the world is a model, fundamentally.
See, I maybe don't want to disagree. I mean, I would, like, following Peirce, I would say that we have this representation, but there's still the something which had to give rise to the representation, and the way that that something was encountered prompted us to represent it in that manner. So we aren't just walking around with pure representations, with pure models. There has to be this something. Like, Peirce has, he characterizes a whole bunch of different philosophies under which categories they ignore. And like, he's really hard on the, like, well, Hegel really, for talking about everything in terms of thirdness. So everything is these representations, these ideas. But without that underlying thing, without the underlying real, the representations just become purely nominalistic. They either become, they either basically stop caring about what they're talking about, or they have to just not pay attention to it. Because if they do start to pay attention to it, then they can no longer just consider themselves pure representations.
Well, thank you so much for this really interesting conversation here. I'm wondering, Jeremy, if this is something that you've been thinking about as you've listened to the conversation, or as you were listening to Tim's presentation.
Not especially. I find philosophy very interesting, but I wasn't following to the extent that I can participate in this conversation, unfortunately. But I really appreciate it when I was hopping in every so often. I have a question. If we still have time, I have a question for Jake.
Please go right ahead.
So I'm really interested in what were the issues you had when initially trying to start with the machine learning? Because it seemed like you said that there were a couple issues that really made this difficult as a task. And I found it really interesting that you guys actually started to use machine learning to generate polymers. So I don't know. It's kind of an open question. It's not a very good one, but
No,
I'd
it
like
makes
to know
sense.
more about it.
Yeah, so like it is a really complicated process. And the reason that we say that it's non-trivial is that by the process of coarse graining, you lose a lot of information. Like if I'm condensing 32 sites to one site, like there's a lot of information lost. So going backwards is really, really difficult. And so that's what makes it non-trivial. So before we even started doing machine learning, we were trying to just algorithmically write code that can try and redo this, like reinsert that information. And it got quite far, but it was never able to fully recreate the polymer system. And so therefore we turned to machine learning. And the difficulties with machine learning is that there are so many different machine learning methods that accomplish different tasks. There are so many different loss functions that accomplish different tasks, and there's so many different ways of representing the data. And those were all decisions that we had to make. So like for the model that I actually presented, like there's 20 models that failed, you know? And so a lot of the things were like, okay, something technical that I didn't mention is that like the outputs that the model predicts, you would expect it to predict like XYZ coordinates, but it's actually not doing that. It's predicting a probability distribution over XYZ.
Oh, okay.
That's more useful to try and model a polymer, because like predicting a specific XYZ coordinates is can be somewhat difficult, but it's still an option for kind of doing this.
Okay. That makes sense. So it took 20 different machine learning algorithms. That's really crazy.
Well, I mean, like not specifically like 20 individual. It's just like we tried a bunch of different variables and methods, and a lot of them failed. Like, and that's just kind of like expected. Like you're constantly tweaking the method and changing how you represent data and stuff.
That's I found that super cool. Yeah. No, thank you.
So, Jeremy, I'm wondering if you could go back in time and start fresh on your project. What would you do differently?
If I could go back in time and start fresh on this, the difficulty with approaching this type of problem is that it's very theory based. So, and and quantum optics is just a really large field. Once you start getting into it, you kind of like are just opening a book midway, and you have to like, I don't know, sort of manage that way, reading pieces and then piecing it together, if that makes sense. I really wish there was an optimal way to approach this issue. If I could go back in time, I would probably read more, and then I mean, it's not very it's not a very satisfying answer, but I think I would rather read more of the resources that have been provided, and just kind of like dive headfirst into a specific area. What I ended up doing was kind of taking pieces, but very shallowly, if you will. I would take a little bit of information, but not really truly understand it. And that's really difficult to make conclusions if you don't fully grasp the material itself. I don't know if that's if that's the I don't know if that's the answer, or not the answer, but really a good answer to your question. But I think that's what I would have done.
I think that's a fabulous answer to that question. Tim, Jake, is there anything? Oh, okay. Rather than one of my questions, we have a question here from our attendees. A question from Luke here. Hey, Timothy, if science operates within the frame of its particular methods and makes models, revealing truth about the object on one hand, but concealing it in another way, how does phenomenology differ methodologically such that it gets to the thing itself? Can it do this?
Sorry, I realized I was talking while muted. Yeah, that's a question I was thinking about when writing this method of, or writing the preface of, how is phenomenology not just doing the same thing, which is just replicating the same problem? And see, like I said, it's not the posing of a theory. It's not the having of a method that's the issue. As you know, as Jake and Jeremy were talking about, like, there's problems that arise. You actually have to pay attention to what the object of study when you're investigating it. You had to go through 20 different iterations to try to get an algorithm that produced acceptable results. And so there's something happening right there. There's an actual result. But the thing is that I guess here the phenomenology and the critique that I was offering with science is that just that it only seems to take it in these mechanistic terms according to the mechanistic laws. And so I think phenomenology less so isn't trying to become that objective nothing that I talked about at the beginning of the preface of somehow, oh, if we just get rid of all of our influences, become this pure slate, suddenly the truth can come into us and it will be all good. I think it's that, well, Peirce's phenomenology, really. I should preface that. Peirce's phenomenology. He says that what one ought to do is to simply go out and say what presses upon the mind. And then there's a couple of faculties that come with it. One of them is seeing what stares one in the face. And this isn't, and to repress what one thinks it ought to be. And so it seems less to me of, it's that, oh, we become the blank slate, but rather we study, the phenomenology allows for the study of how it is that one cognizes the object, such that it's not, it doesn't have to do with not having anything, but through the distortion, or maybe not distortion, but through the comportment, through the structures of cognition. By studying that, what we can get a good basis for starting to investigate the actual objects that appear in front of us by being aware of the way they arise in the mind. So I think it has some possibility, although I don't know if this is the method. I think that like that is a remaining question of how exactly we are to inquire. And I don't think that this is like somehow the answer. I think that is a question that's going to take, if it'll get an answer, if I'll have an answer eventually, will take a lot of time, and give it another 100 years and somebody else will have another way that is different than that. So that's kind of think that's one of the perennial issues that always arises.
Great, thank you very much. Right. Were there other questions from our attendees? Please feel free to put them in the chat. So I was wondering, maybe Jake, you could start us off if you could tell us kind of what's up next for you in research and in your life.
Sure. Well, I'm trying to finish up my research project. It's part of my thesis for the Honors College. And so I'm writing a thesis with it and have to do a presentation. Hopefully I'll be able to work on it a little over the summer as well to try and get into a more final state to move on to other members of the lab. I'll be going to UCLA for graduate school in the fall. So that's kind of what's up next for me in terms of research and moving forward.
Congratulations. Tim, how about you?
Yeah, I'd like to, well, I'm also finishing up my thesis, though it's just for the department. Dr. Scott Pratt, who asked the question, is actually my thesis advisor. So I was nice to see him here. I intend to go to graduate school. I was taking a year off in between undergrad and graduate, and then this whole virus happened, so I have no idea what the next year is really going to look like. I don't know, probably mostly trying to get into Aristotle in more detail, because I think at a certain point in my research, there was a point where Peirce spent so much time studying Aristotle that I couldn't understand more of Peirce without understanding more of Aristotle.
And Jeremy, what's next for you with your research in your life?
So I plan on continuing this research into the next year, and then I will be graduating June or summer of, actually, no, it wouldn't be summer, it would be June, but June of 2021. And I plan to apply to grad school. I'm thinking about maybe going to UW or UC Boulder, but yeah, no, I plan on just continuing with research. It seems to suit me.
Fabulous. Well, I think research seems to suit all of you. This has been a fantastic panel. If there are any questions from our attendees here, I think I'll give it one more minute. And please forgive the dead air here, both on the recording and for folks who are attending. And panelists, last chance if you'd like to ask any questions of each other.
I actually have a question for you. So for the recording, is it going to be distributed out like via YouTube, or how else can we get a hold of it?
I believe it's going to be on YouTube. McKenzie, can you correct me on that?
Yes, it will be on YouTube. It'll be on the U-Oregon YouTube page, and there will be a sequence for all of the sessions that were presented and recorded today live, as well as these individual recordings. So you can find that. We're hoping to get it live by tomorrow, but you'll probably see them start getting uploaded over the weekend as well.
Okay, cool.
Fantastic. Well, thank you all so much for a wonderful panel and for your great questions and for this fantastic discussion. And I hope everyone